Just one player. What is the Laplace strength of this? Where it's like zipping, right? And the front is gonna be like right here.
Yep.
Right here.
It'll be up on top too. Yeah, I think there's a typo on this part, the part A in the homework, I think, right? Yeah, I think there was a typo in my solution. So I can put back and check them. But you need an S plus 4 on top too.
Yeah, right here, right?
Mhm.
Like everything with an S is gonna be the plus one.
Exactly. Mhm.
Thank you.
Yeah, I did. Your jokes. This was one of those. Well, that's what happened. That's- This-
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so today it's just more Laplace stuff, and so we'll be doing Laplace for a while. So today I have a couple of examples just showing you how to do solve differential equations with Laplace transforms. So it's kind of just one example we started last time. We're gonna finish that up, and then another example for that. And then we're gonna be moving on to step functions, which are, a type of forcing function that we can only really do using Laplace transforms. Okay. Okay. Announcements. So homework 3 was posted on Tuesday night. I did make some mistakes in my solution. So I think for problems 2A and 2C, I think there are some typos in my solution. So I need to go back and correct those. So if you're working on that and you're not getting what I'm getting, then probably it's because I made a mistake. So I'm gonna go back and correct those, and I'm gonna put an updated homework solution or homework problem set online once I fix that. Probably is gonna be sometime tomorrow. Just because next for today and for tomorrow morning I'm pretty booked. So but yeah, just keep on the lookout for that. Okay. So homework 3, I don't know if I mentioned this last time. Homework 3 is going to be the last homework we have before the first midterm. Laplace is going to be the last kind of big topic we cover before the first midterm as well. So homeworks 1, 2, and 3, you can expect, those are going to be the ones covered for the first midterm. We'll talk more about the midterm probably starting next week. The midterm is not planned until March 6th. So that's, not next week, but the week after that. So 2 weeks from today. But next week we'll talk on more specifics in terms of what to expect, the format of the exam, what you can bring, things like that. Okay. All right. Any questions I can answer before we get started? Okay. All right. So let's pick up where we left off last time. Okay. So we were talking about solving ODEs using Laplace. Okay. So, for the last 2 lectures or so, we've introduced this idea of Laplace transforms as an alternative way to solve differential equations. Okay. Now, there are some benefits and some downsides to this. There's a common phrase that we have in engineering that said there's no free lunch, and so there's no easy way to do all these things. So I won't say that solving these problems with Laplace is better or easier than the traditional way. It's just kind of an alternative way to do it. Okay. And so there's usually a 3-step process that we go through to do this. And so step 1 is to take the Laplace transform of the entire differential equation. Okay. So that includes all the derivatives, all the forcing terms, and make sure you carry all the coefficients there as well. Okay. Step 2 is once you take the Laplace transform of the entire equation is to use algebra and solve for the solution in the Laplace domain. So traditionally, we use the symbol y for our solution. So you're going to be solving for the function y of s in your solutions. Okay. Along the way, you may have to use partial fraction decomposition before doing the third step. So last time, we had a lot of fun relearning how to do partial fractions. And then step 3 is to basically just take the inverse Laplace. Okay. So we're going to take the inverse Laplace of y of s, and that's going to give us our solution finally back in the physical domain, y of t. And remember the traditional way, the way that we take Laplace transforms and inverse Laplace transforms is we match up the terms according to what's in the table. Okay. And so we basically manipulate these expressions algebraically to get it to look like something in the table, maybe apply partial fraction decomposition if we have to. And then once we get them matching up, we just use the table to perform the inverse of the Laplace transform. Okay. All right, so to that end, we're working on this example, and we kind of worked on this example all through the class last time, so I'm just going to write it from scratch again. Okay, so for this example, we had the following differential equations. You had y double prime minus y is equal to t. Okay, so fairly simple equation, and we're going to subject it to the following initial conditions. So we have y of 0 is equal to 1, and y prime of 0 is equal to 1 as well. Okay. All right. And so we want to solve this ordinary differential equation using Laplace transforms. All right, so let's follow our three-step procedure that we've kind of outlined above there. So first, let's take the Laplace transform of this entire equation. Okay. And so we're going to take the Laplace transform of each individual term. Remember, Laplace transform is a linear operator, so that means we can all the rules of linearity apply to it. Okay, so we're going to take the Laplace transform of y double prime minus Laplace transform of y is equal to the Laplace transform of t. Okay. All right, so let's go ahead and evaluate these expressions. So first we have the Laplace transform of y double prime. So that is the Laplace transform of a second order derivative of a function. Okay. And so this is going to be s squared y of s minus s y of 0, initial condition, minus y prime of 0. Okay. So this right here comes from that. Okay. Next, we have Laplace transform of y by itself. So y is our solution variable. So then we take the Laplace transform, we just get y of s. Okay. And then finally, we have the Laplace transform of t. And so according to our table, this is equal to 1 over s squared. Okay. All right. Let's go ahead and plug in all of the initial conditions because we have those given to us in the problem. So first we have y of 0, that's equal to 1, and then y prime of 0, that's also equal to 1 as well. Okay. So plugging that in, we get s squared y of s minus s minus 1 minus y of s is equal to 1 over s squared. Okay. All right, so now that we've taken the Laplace transform of the entire equation, we've plugged in the initial conditions. Let's go ahead and solve for y of s. Okay, so this part here just involves algebra. So first thing I'm going to do is I'm going to take this s minus 1 and move it over to the other side. Okay, so we're just going to add an s and add a 1 to both sides. And then for the y of s, I'm just going to group those together and factor out that s squared minus 1. Okay, so on the left-hand side, we have y of s multiplied by s squared minus 1 is equal to 1 over s squared plus s plus 1. Okay. And then let's go ahead and divide both sides by s squared minus 1, just so that we isolate the y of s on the left-hand side. Okay. And so we have y of s is equal to 1 over s squared times s squared minus 1 plus s plus 1 over s squared minus 1. Okay. I'm going to group those last two together just because, if you remember from last time, we're going to have something cancel out. Okay. All right. So the next step in this process is going to be to take the inverse. But in order to do that, we need to get everything in a form that's convenient for us to take that inverse. Okay. Okay. So first thing I'm going to do is let's take the second term here, just because we know that s squared minus 1 is equal to s plus 1 times s minus 1, right? That's just our kind of our algebraic identity of, a squared minus b squared is equal to a plus b times a minus b. Okay. And so with that, we can see we have an s plus 1 on the denominator, cross cancels out with the s plus 1 on the numerator. Okay. So then this term just becomes 1 over s minus 1. And 1 over s minus 1, this is something we can invert because this is just the inverse Laplace transform of e to the t. So we can say this invert, yes. So that term is good. So that term, we don't have to worry about it. So we can just leave it that as it is, and then we can just invert it at the end. Okay. Don't forget about it though, because sometimes when you do partial fractions, I think it's easy to kind of forget about the terms you left behind. So don't forget about it. Make sure you bring it down to the bottom. But that term as it is right now is in good shape. Okay. All right, and then we have this term, which is kind of where we left off on Tuesday. And so in order to get this into a form that we can take the inverse Laplace transform, we have to apply partial fractions. Okay. So that's kind of just where we were on Tuesday. So this is just kind of a quick recap. I know I went through the first part of that example kind of fast a little bit, but that was kind of what we did already on Tuesday. Any questions up until this point in the example? Okay, so let's get started with the partial fractions then. Okay, so for partial fractions, let's break this up. So we have 1 over s squared times s squared minus 1. Okay. All right, so we want to break this up into its components, component pieces. Okay. All right. So this is actually going to break up into 4 separate fractions because what we have here is we have 1 over s squared. So this right here is a repeated root. Okay. So we basically have 1 over s twice in the denominator there. And so if you recall from last time when we have a repeated root that we break it up into all of its component pieces, which includes all the lower order terms as well. Okay. So that means we're going to have one term in our expression, which is just a over s. Okay. And then another term, b over s squared. Okay. So we basically include every single repeat of that root. So s and s squared. All right, and this other term right here, is a quadratic. Right. So it's not a repeat root because it's, s squared minus 1. But it is something, it is a polynomial that is, of quadratic order. And so when we break this up or when we decompose it, we have to include a linear term in our numerator as well. Okay. And so the partial fraction decomposition of this one is going to be cs plus d all over s squared minus 1. Okay. So, we kind of started with a relatively simple term, but a four expression partial fraction decomp is not trivial. This is not usually a comfortable thing to do. Okay, but let's go ahead and start solving this because essentially we want to solve for the values for a, b, c, and d. So first thing I'm going to do is let's go ahead and multiply this entire expression by the denominator. And so we're going to multiply by s squared times s squared minus 1. Okay. And so if we do that, we have 1. So that's going to cancel out with all of the denominator on the left-hand side. on the right-hand side, we have A times S squared minus 1 plus B times S squared minus 1 plus CS plus D multiplied by S squared. All right, so let's distribute all of those terms through. And then what we're going to do from there is we're going to group the like terms together in terms of S, just like we did on Tuesday. Okay. All right, so on the left-hand side, we have 1 is equal to AS cubed minus AS plus BS squared minus B plus CS cubed plus DS squared. All right. So let's group terms. So let's group terms in terms of the powers of S that they have. Okay. So we have 1 is equal to. Let's look at all the S cubed terms. We have A plus C. I think those are the only S cubed terms that we have. Okay. And then we have the S squared terms. So for S squareds, we have B plus D. Okay. Then we all have all the terms that are multiplied by S. We have a minus A. And that's it. And then we have all the constant terms, which is just minus B. Okay. Okay. So now that we've grouped all the terms here, we can set up our system of equations. We can just basically match up power terms on the left-hand side and the right. And so on the left-hand side, we have a fairly simple result. We just have 1. So that means all of the S cubed, S squared, and S terms are all going to be equal to 0. Okay. Okay, so let's look at the equation for S cubed. Okay, so we have this is A plus C is going to be equal to 0. Okay. Equation for S squared, we have B plus D is equal to 0. Okay. For the S terms, we have minus A is equal to 0. And then for the constant term here, we have minus B is equal to 1. Okay. So this, even though there's 4 equations, 4 unknowns here, but this actually has a pretty simple result. Because right off the bat, we can see that A is going to be equal to 0, right? B is going to be equal to minus 1. Okay. So those are pretty easy equations to work with. Okay. We can then take this result of A is equal to 0, plug it into this equation here. And so if A is equal to 0, that means C must equal to 0 for this equation to be satisfied as well. Okay. Because we have 0 plus 0 is 0. Okay. Then from this equation here, you plug in the fact that B is equal to minus 1. The only way to make this true is if D is equal to 1. Okay, so now that we've successfully done our partial fraction decomposition, we can go ahead and plug this back in for y of s. Okay. And so y of s is equal to, we have minus b, so minus b is a minus 1 all over s squared. Okay. Plus d is 1, so that's 1 over s squared minus 1. And then let's not forget our extra guy, which is 1 over s minus 1. Okay. So these first two terms were from the partial fraction decomp. And this guy was, just along for the ride. So we figured him out before. We just needed to remember to bring him down. All right. So now that we have the entire expression in this form right here, we can just go ahead and invert, okay? Because everything here is in the tables. Okay, so we can finally do step 3. Take inverse Laplace. Okay. And so we take the inverse Laplace, we get y of t is equal to inverse Laplace of -1 over s squared, so that's a minus t, plus inverse Laplace of 1 over s squared minus 1, that is hyperbolic sine of t, plus inverse Laplace of 1 over s minus 1, and so that is e to the t. All right, and so there you have it. So that is the solution to this differential equation using Laplace. Any questions on this result here? Okay, good. And so if you notice here, once we kind of arrive at this point, this is kind of our full solution. So our initial conditions have already been incorporated into this problem, as well as the forcing term too. Okay. If you remember kind of from the traditional way of solving these differential equations, applying the initial condition and solving for the particular solution, those were kind of separate steps or separate things that you had to do. But from Laplace, it's all kind of solved at once. Sometimes, sometimes partial fraction can kind of be annoying to do, but, everything is kind of already included. So, you don't have to kind of do extra stuff. Okay. All right, so let's do another example of this. This one kind of showcases some different stuff. All right, so for this example, let's look at the differential equation y double prime plus y prime plus 9y is equal to 0. And let's look at the initial conditions. Y of 0 is equal to 0.16, and then y prime of 0 is equal to 0. Okay. All right, so just like we did with the last example, let's go ahead and solve this equation using Laplace transforms. Okay. All right, so first step, let's go ahead and take Laplace transform of this entire equation. We have Laplace transform of y double prime plus Laplace transform of y prime plus 9 times Laplace transform of y is equal to 0. Well, Laplace transform of 0 is just 0, so I'm just going to put 0. Okay. So this one, we have no non-homogeneous term, so our right-hand side is 0. So we have a homogeneous problem. We're trying to avoid the double negative there. But you're going to see this one has kind of an interesting solution. Okay. All right, so let's go ahead and apply these. So we have a Laplace transform of a second order derivative. So we know that's s squared y of s minus s times little y of 0 minus y prime 0. Okay. plus a Laplace transform of the first order derivative. So this is something we didn't have last time. So this is going to be s y of s minus y of 0, little y of 0. And then we have a Laplace transform of 9y y, which is 9y of s. Okay, so let's go ahead and plug in all of the initial conditions here. So first one we have here is y prime of 0 is equal to 0. And so this one is just going to be equal to 0 here. Okay. And then for y of 0, we have an oddly specific decimal here, which is 0.16. Okay. Okay, so let's go ahead and incorporate all of those. Okay. I'm going to factor out all of the terms that have y of s in there as well. So we have y of s multiplied by s squared plus s plus 9, okay, minus 0.16 s minus 0.16. And all this is equal to 0. Okay. All right, so now that we plugged everything in, all of the initial conditions, let's go ahead and solve this equation for y of s. So that's step 2 of our procedure. So solving for y of s is pretty straightforward here. And so everything, so the 0.16s and the 0.16, I'm just going to move those to the other side of the equation. And then I'm going to divide the entire equation by s squared plus s plus 9. Okay. All right, so doing so, we get y of s is equal to, I'm going to factor out 0.16. So we have 0.16 times s plus 1 divided by s squared plus s plus. So I kind of combined a couple algebraic steps into one for that. Okay, good. All right, so now that we have an algebraic expression for y of s, the next step here is going to take its inverse. So we're going to take the inverse Laplace of this expression here. All right, but we come to an interesting situation here because we have a denominator here, s squared plus s plus 9. That is a quadratic function, but that doesn't quite match up with anything that we have in the table, nor can we take a partial fraction of this. So this is a quadratic function, not in table. Okay. And since this is not a product of s times something else, or then this is something we also can't factor, or also we cannot decompose. All right. So we need to do something to this, and so we need to get it into a form that's good. Okay. So usually when you have a quadratic function like this in the denominator, the way that you can get into a form that matches the table is to complete the square on the bottom. Okay. So let's go and do that. So we have y of s is equal to 0.16 times s plus 1. Okay. So on the denominator, I'm gonna complete the square. And what that's going to do is that it's going to put the solution in a form that's going to match up with something in the table. Okay. All right. So you have s squared plus s plus 9, right? And so what we're going to add So the way we're going to complete the square is we're going to take the coefficient in front of the s, which is just 1, right? We're going to divide that by 2. And then we're going to square, right? Remember, that's how we complete the square. All right, so we're going to end up with a little bit of an awkward number here because that number that we need to add to complete the square is 1/4. Okay. So to complete the square, we need to do s squared plus s plus 1/4. Okay. Because what this is going to do, this is going to factor out into s plus 1/2 quantity squared. Okay. But then to complete the square, we also need to subtract 1/4 after the expression. Okay, so we're going to add 1/4 to complete that square, and then subtract 1/4 afterwards, just to make sure we keep, we keep the same overall value. Okay, and we can't forget about the +9 either as well. Okay, so if we simplify this, so first of all, we're gonna take that square, so that's we're gonna replace that with the square. And then we need to evaluate 9 minus 1/4, which is a very awkward 35/4. So you have 0.16 s plus 1 divided by s plus 1/2 quantity squared plus 35/4. All right. But at least we're getting somewhere now, because now this denominator that we have, right? We basically have the sum of a squared factor here, plus another term. So this denominator looks like the denominator of a exponential multiplied by a sinusoid. Okay, in other words, a shifted sinusoid. Okay. All right, so now the trick, or now what we need to do is we need to get the numerator into the appropriate form so that we can take the inverse according to the table. Okay. All right, so let's kind of remind ourselves what the transforms for these actually look like. Okay, so if we look in the table, the transforms for this is that we have e to the minus at cosine of omega t. Okay, the transform for this is s plus a divided by s plus a quantity squared plus omega squared. Okay, and then e to the minus at sine omega t. The transform for this is omega divided by s plus a quantity squared plus omega squared. Okay. So basically, we're going to try to manipulate this expression so that we have something that looks like this. We're very close, and so we're quite close to this. It's just kind of just moving some terms around a little bit in order to get it to match up exactly. Okay. So this right here is from the table. And we want to try to get these from our expression. Okay. All right, so first, since we're almost there, let's try to get cosine first because we need to have s plus a up on the numerator. Okay, and so if we look at our expression here, our a value from what we see here, our a value is going to be 1/2, right? Right. It has to be just because that's just how we completed the square on the denominator. So we want to manipulate the numerator up here so that instead of s plus 1, this needs to be s plus 1/2. Okay. Okay. So let's do that first. So if we do that, we get 0.16 multiplied by s plus 1/2 divided by s plus 1/2 quantity squared plus 35/4. Okay. And then in order to make this compatible with the previous one, we need to add another 1/2 as well. So this is going to be add 0.16 times 1/2 divided by s plus 1/2 quantity squared plus 35/4. Okay. So I basically took that s plus 1 that was in the numerator there and kind of split it up into 2 so that on the left-hand side here, right, this is the cosine. Right. That's good. So that's something we can use. And on the right-hand side there, we have sine. Okay. Okay. And so if we do this, we can already invert that one. And let me just go ahead and evaluate this numerator here. So this numerator here is going to be 0.16 times 1/2. And so that's just going to be 0.08. Okay. All right. And so just like we did last time, we need to change this so that we have omega in the numerator. Okay. And so based on our denominator here, the term that we need to get in the numerator is square root 35/4, right? Because that 35/4 there represents omega squared. Okay. So we need to get this in the numerator so we can take the inverse with respect to sine. Okay, and so if we do that, we get, I'm going to go ahead and pull out that 0.08. Okay. I'm going to divide this by square root 35/4. Okay. Just so inside here we have square root 35/4 divided by s plus 1/2 quantity squared plus 35/4. So we put that omega term in the numerator, and then just to keep things kind of balanced, we divided it again on the outside. Again, whatever we have on the outside, that can just be carried along when we take the inverse. But we need to make sure that whatever's in the parentheses matches the form that's in our Laplace table. All right, any questions on any of the things that we did in this step here? Yes.
When we like take the 1/2, the 16 and the 0.16 and the 1/2 to the other side, is it always going to be in that form?
Well, sometimes you might have to subtract. And so in this case, we had s plus 1 in the numerator. And so you can see here, we just kind of took half of that and kind of borrowed that for the cosine. And just whatever was left over we took to the other side. But sometimes you might have to subtract because sometimes you might have, instead of s plus 1 in the numerator here, when I say you have s minus 3 or something, right? But in order to take the inverse of this, you need to have s plus 1/2 up top. And so what we're going to do instead there is that we'd have 0.16 s plus 1/2 divided by the denominator, which I'm not going to write out because it's really long. And then on the right up here, we would have minus 0.16 times 3.5. Just to kind of keep things balanced. And so if you want to check to make sure if you did your kind of your algebra correctly, just actually kind of simplify it, and it should simplify to whatever you started. Yeah. So in this case down here, if we simplify this, we kind of turn this back into 0.16 times 1/2, right? if we actually added these two things together, you know, we should get back our s plus 1 on the top right. Yeah. Any other questions on this stuff here? Okay. All right, so let's go ahead and take the inverses because now these are all ready. Okay. So we take the inverses. So this is 3, take inverses. And so take the inverse of this, we get e to the minus 1/2 t times times a 0.16 cosine of square root 35 over 4 times t. Okay. So that's the inverse Laplace of that first term there, plus 0.08 divided by square root 35 over 4 e to the minus 1/2 t times sine square root 35 over 4 times t. This one's a little bit of a mess. So, you know, having square roots around is usually not a recipe for a clean solution. But, you know, I like this example because I think it showcases a lot of things that we didn't do in the previous one. So, you know, we didn't do partial fractions here, but we did have to do a lot of manipulation in order to get things into the exact right form to take the inverse Laplace. Okay. All right. So I do have actually quite a few more examples, and so if you go on the Canvas site, you'll see that there's actually an additional handout called, I think it's called Lecture Note 03A, more Laplace examples, and so there's definitely a lot more of these. So the thing, you know, like I mentioned, the thing with Laplace is that, you know, you just have to kind of practice it a lot, see it done a lot of times. That's kind of how you get the hang of it. We only have a limited amount of time in the class, and so, you know, I can't really go through a ton of these. Also just because they're a little bit time consuming, but definitely check out the extra examples on Canvas so that you can get some more practice. Okay. All right. And so with that, let's go ahead and move on to kind of part 2 of this Laplace journey here. Okay. So now that we kind of know the basics of how to take Laplace transforms and solve differential equations with Laplace, we can kind of start to do some more interesting things with the Laplace transforms, right? And so this next set of notes that I think we're going to go over today on Tuesday and maybe half of Thursday next week has to do with some special non-homogeneous terms, or so special forcing functions. Okay. So first of all, you know, let's kind of remind ourselves what a forcing function is. Okay. So a forcing function in an ordinary differential equation is another term that I like to use for the non-homogeneous right-hand side. Okay. So if we look at our kind of our traditional second order ODE, we have y double prime plus py prime plus qy is equal to r of t. Okay. This r of t here, you know, this is our forcing function. And if you think back to homework 2, you know, the forcing function there is largely responsible for the steady state behavior of the solution. Okay. Because for almost every kind of, physical system that's governed by second order ODE, we have the transient solution that's usually governed by the initial conditions. And then we have the steady state solution that's governed by the forcing function. Okay. So the forcing function plays a very important role in a lot of systems, and in a lot of ways, you can't really, it's a fundamental part of whatever solution that you get. Okay. Now, the unique thing about Laplace transforms is that it gives us a way to deal with, I would say, kind of special forms of this forcing function. Okay. So the first form of the forcing function that we're going to look at are what are called step functions. So step functions are special functions that are used to model behavior that can be turned on or off. And so there's kind of a binary kind of behavior to these things. So mathematically, you've probably seen them. And so mathematically, they look something like this. Okay. And so they look just like kind of a step function that just looks like that. Okay. So usually at some time t naught, the step function is activated. So when the step function kind of steps up, we say that it's activated. And of course, the step function gets its name because visually it kind of looks like a staircase step that you can step up on it. Okay. Okay. So this function right here, which steps up at t0, the way we denote this is we use the function u. So u is a function that's used to denote a step. And so this is denoted by u of t minus t naught. So this is a step function that starts at t naught. Okay. So how is this special, or how can we use this? So a lot of times, in engineering systems, there are forcing functions or some external forces that are turned on and off. Okay. So for example, let's look at an electric circuit with a battery and a switch. Like it's spelled. Switch. Okay. And so let's say we have a circuit. This will be a simple RC circuit. So we have a resistor, a capacitor. Okay. We have a source here. So let's say we have a DC circuit. And let's say that this circuit also comes with a switch. So basically, you can turn the switch on and off, right? So turning the switch on will connect the circuit, will connect the battery to all the components. Turning the switch off will disconnect the circuit and kind of remove any kind of battery force, right? So this is a very simple diagram of how a light switch typically works. Okay. Okay. So let's look and see what happens when the switch is on and versus when the switch is off. So when switch is on, okay. So when the switch is on, the battery is fully connected to the entire circuit. Okay. And when the battery is connected to the circuit, what's going to happen is that the capacitor is going to start to store charge. So basically the battery is going to be supplying power to the circuit and the circuit's going to start charging. Okay. All right, so when the switch is off, okay. When the switch is off, the battery is going to be disconnected. Okay. And what's going to happen to whatever charge was on the capacitor, it's going to start to discharge. And so it's going to start to kind of release that power. Okay. So we have kind of two different kind of fundamental behaviors for the same circuit, depending on whether that switch is on or off. Okay. Okay. So normally, if you wanted to analyze, if you wanted to kind of or model a system like this, and you were to kind of do it the traditional way, you would have to kind of solve the problem twice. And so you have to solve the problem once for, the case for when the switch is on, and then you'd have to solve the problem again for when the switch is off. Because technically speaking, between these two situations, the governing equation actually changes between. Okay. So since each has kind of a different governing equation, you'd have to solve the system twice. All right, question. So once the capacitor is fully charged and it acts like a wire, would that have to account for that? Yeah. So that's something that you can that's accounted for too. So if you leave the switch on enough, basically the capacitor is going to get fully charged, and so at that point, the system kind of just reaches steady state. And so if you wanted to look at a situation where you turn the switch on, then off, then on, then off, then that would have to be something that you have to account for too. But kind of no matter what, whether you let the capacitor fully charge or you stop it beforehand, you have basically two different equations to solve. And the way you kind of solve one, you go from one to the other, is you kind of pass the initial condition from one state to another state. It's not a convenient thing or a smart thing to do in general. Okay. But that is a good observation that once the system reaches steady state, then that does have to be taken into account as well. Okay. Okay. And this circuit is not the only case for this as well. And so another case where it's a little bit more complicated, but but it kind of follows the same principle is take just driving your car down the freeway or something, right? And so when you're driving your car on the freeway, or you're driving your car on the road, you're not stepping on the gas at all points of time that you're driving. So there's a lot of times when you're driving, you kind of take your foot off the gas, you kind of let it coast. Especially if you're going downhill, you're not applying gas all the time, because otherwise your car would just keep accelerating, and the police would give you a ticket, which is not fun usually, right? And so that's another situation where you have forcing that's kind of turned on and turned off depending on when you turn on the gas pedal, right? And so to solve a situation like this, or to solve cases where you have forcings that get turned on and off, in the traditional way is really not kind of practical and really kind of annoying. Okay. And so what we can do is we can take these situations and use a step function to model the forcing. All right, so for example, let's take the difference between two different step functions, each one that are being activated at different times. All right. So let's say we take u of t minus t naught, and from that we subtract u of t minus t1, okay, where t1 is greater than t naught. Okay. All right. So let's see what this looks like. And so we have, first, let's look at u of t minus t naught. So this is a step function that starts or that gets activated at t naught. Right, so let's say t naught is right here. This is a step function that looks like this. Okay. And then let's also look at u of t minus t1, where t1 occurs at some time later. So if we look at this here, let's say this is t1. This occurs somewhere beyond there. Okay. And let me mark t1 on this other plot as well. Okay, so let's say we have t1 is somewhere over here. Okay, and so if we subtract another step function that occurs at a later time, what that's going to do is that it's going to basically take out or eliminate everything beyond that second time, right? And so in other words, we're going to have a step down at this time, okay? And then everything on the right here is going to be 0. All right, and so by taking the difference between these two step functions here, what we've done is we've created what's called a square pulse, right? And so this square pulse is a signal or a function that gets activated at t0, or in other words, we can say is turned on at t0, and then at t1 it is then deactivated or turned off, right? And so this is something that can be model something that's turned on and then turned off. And so this is what we call, technically, I hate this name because the technical name for this is a square pulse, but most of the time it's not a square because it's you know, the length of this can vary. So you know, the kind of I guess the more accurate term for this would be a rectangular pulse. Right? Something that's only active for kind of a short period of time. But technically, if you look this up in textbooks and stuff and papers, you know, this is called a square pulse. But it's not a square. It's oftentimes rectangular, oftentimes a very long rectangle too. Okay, so this is good. So you know, we can use these step functions and these, you know, pulse functions to represent forcing that can turn on and off. Okay, but how does this relate to Laplace? Well, it turns out, you know, you can actually take a Laplace transform of a step function. Right, so you can take the Laplace transform of u of t minus t naught, okay? And so this is one, I know for the most part, we just look at the table, but this is one that I'm actually going to show you the actual derivation because it is kind of cool, okay? All right, so if we plug this into our formula for the Laplace transform, what we have for this is, remember, Laplace transform is integral from 0 to infinity of the function u of t minus t naught times e to the minus st dt. Okay. Okay. Good. Now, this step function is a very unique function to integrate because it's in technically speaking, it's a discontinuous function. And so it's 0 all the way up until you reach t naught. And then once you reach t naught, it jumps up to a value of 1. Okay. And so since this is a discontinuous function, in order to properly perform this integral from 0 to infinity, we actually need to break up the integral into 2 different regimes. So we need to break it up from the section from 0 up until t naught, and then from another integral from t naught up into infinity. Okay, so this is going to break up to integral from 0 to t naught well, during this stage from 0 up until t naught, the step function is 0. Okay, times e to the minus st dt plus integral from t naught to infinity of 1 times e to the minus st dt. Okay, so let's evaluate these integrals. And so the first integral, we have 0 times e to the minus st. So no matter what the integration bounds there, that's going to be 0. Okay. That makes sense because the step function is just not activated or not turned on until t naught anyway. And so everything up until t naught, we just kind of just ignore. Right? Okay. This second term we can integrate. So let's go ahead and do that. So we have minus 1 over s multiplied by e to the minus st evaluated from t is equal to t naught to t is equal to infinity. Okay. So if we evaluate this at the integration bound, we have minus 1 over s times e to the minus infinity minus e to the minus t naught times s. So we have e to the minus infinity asymptotes to 0. So we can just assume that this just kind of goes away. Okay. T naught is just a constant, and so we just kind of leave it there. And so, but we do have these 2 negatives cancel out. And so if we do that, we get a Laplace transform of u of t minus t naught is equal to e to the minus t naught times s divided by s. All right. And so if you look at this function right here, it looks like the Laplace transform of 1. So if you recall from last week, right? At one point, we took the Laplace transform of just a constant function 1, right? And so the Laplace transform of 1 is just 1 over s. And so this looks very similar. And so we do have that 1 over s there. But you can see here that we have this additional exponential term on the numerator that has to do with the fact that this step function is shifted by that amount. Okay. So these two are very similar, which makes sense because a step function is essentially just 1. It's just a delayed 1. So it's a 1 that kind of starts. It doesn't start at t is equal to 0. It starts at some later time. Okay. So I want you to think of the step function kind of like that. So this is like shifted function of 1. And in fact, this idea of shifting and using the step function to shift kind of forms the basis of our next shifting theorem. All right. Any questions on this? Okay. All right. So last thing we'll cover today before we head out is we'll introduce this idea of the second shifting theorem in Laplace. And so the second shifting theorem, oftentimes we call it the T-shift, as it ends up being kind of a shift in the time domain. Okay. So before we go over the second shifting theorem, let's review our first shifting theorem. So the first shifting theorem sometimes is called an S shift. Okay. Okay. So for an S shift, the way it worked was that if we multiply our function in the time domain, if we multiply a function in the physical domain by an exponential function, and so by multiplying a physical domain function by an exponential, what that essentially does is that it shifts the Laplace transform by an amount of that exponential. So remember, it looks something like this. So if Laplace transform of f of t is equal to big F of s, okay? So if that's true, then the Laplace transform of e to the minus at f of t is equal to f of s plus a. Okay. So a multiplication of an exponential in the time domain, in the physical domain, led to a shift in the S domain, hence this name S shift. Okay. Okay. So the second shifting theorem is very, very similar, except it's going in the reverse direction. Okay. So for a T shift, our second shifting theorem, if we multiply by an exponential in the Laplace domain, that's going to lead to a shift in the physical domain. Okay. So it's literally just kind of the opposite of what's there. Okay. The difference here is that, you know, we need to factor in our step functions into the result as well. Okay. Okay. So the mathematical form, or the succinct form of the second shifting theorem, is the following. So it starts the same way as the first shifting theorem. So if we know a function f of t and we know its Laplace transform f of s, so let's say if Laplace transform of f of t is equal to f of s, right? So in other words, we have a connection between a certain function in the time domain and a function in the Laplace domain. Okay. Then, and I'm going to swap this just to make it a bit more clear. If we take e to the minus as times f of s in the Laplace domain, okay. So we basically take our Laplace function and we multiply it by an exponential there, okay. Then this is going to be equal to, this is the Laplace transform of f of t minus a. So basically we're shifting the time by the same amount that's in the exponent times the step function u of t minus a. So you multiply by the exponential in one domain, it leads to a shift in the other domain, okay? Now, the main thing to be careful for here are the signs, right? And some of you may have picked up on this already. But if you look at the first shifting theorem, notice how when we multiply by the exponential in the physical domain, I use a negative number here, right? So I use e to the minus at. That led to a positive shift in the Laplace domain, right? So multiplying by e to the minus at leads to a shift of s plus a Laplace domain, okay? For the second shifting theorem, the signs are actually the same. So you multiply by e to the minus as in the Laplace domain. That leads to a minus shift in the time domain, right? So I think that's the part I think that confuses people the most, is that, you know, for first shifting theorem, the signs swap. So you multiply e to the minus at, that becomes s plus a. For the second shifting theorem, the signs are the same. So you multiply e to the minus as, you shift by a minus a in time. Okay. Any questions on these? Yeah.
In the second shifting theorem, if we multiplied it by a positive, would the sign in the step function also change?
It would, yes. Yeah. So whatever sign that's in this exponent here, it's going to match there. So you multiply e to the positive as is going to be f of t plus a times u t plus a. Yeah. Okay, so let's do one very, very quick example, just I know we're just about out of time. Okay, so let's look at the function f of t is equal to 5 sine of t. Okay. And so if we take the Laplace transform of this, we have f of s is equal to 5 over s squared plus 1. All right. So that's just kind of ripped right from the table. All right. But let's say that we kind of redefine f of s, where we take the exponential of that. So let's say that we take, or we multiply by an exponential. So let's say we multiply by e to the minus 2s multiplied by 5 over s squared plus 1. Okay. And then let's say that we wanted to take the inverse Laplace of this quantity here. And so in order to find the actual inverse here, we have to apply our second shifting theorem. Okay. So the second shifting theorem basically says that this result is going to be 5 multiplied by sine of t minus 2 multiplied by u of t minus 2. All right, and so when we come back on Tuesday, we're going to do some more examples with this. We'll see some actual, applications of this for engineering problems. We'll see, actual step functions used in an equation, and see how that affects the results. And next week, we're going to go over another type of special function called an impulse function. Okay. All right, so thank you guys for coming today. I hope you guys have a good weekend, and I will see you guys on Tuesday. Oh, by the way, Aaron, are you here today?
Yeah.
Okay, I have your homework. Oh, great.
Kind of a random question. Like PID too,
Remind me what that is again?
like proportional integral, it's for like the feedback loops.
Oh, a long,
So-
long
so-
time ago. Yeah, yeah.
To stop like over and under damping.
Yeah.
Okay, how a system which makes a funny noise.
Yeah.
It's a linear actuator, it goes up and down.
Okay.
I'm not the one running it.
Uh-huh.
It's the robotics like engineering team that I'm a mentor for.
That's awesome. That's cool.
So the linear actuator, you see like goes up and down.
Yeah.
Something is wrong with the down
Okay.
because the motors make a funny, you can kind of see there's like a small oscillation.
Okay. I see.
My question would be like, I don't know, is it like, I kind of recognize like, oh, it's probably like,
Probably, yeah, that's probably, yeah. You grease the system, that might be,
yeah, it's recently.
okay.
Like, for tuning it, which values are more important to change, or would you know?
Probably whatever controls the damping, I would say, is that's usually going to have the biggest impact on you know, any kind of over damping or any kind of vibrations that it has.
Yeah,
The thing I would change is the overall stiffness of the system. You can change that, like any kind of like oils or springs that they use to tune the system. Over here.
yeah, we use constant force springs to help
Okay.
fight gravity.
Yeah. So that you might want to maybe make those a little bit, maybe a little bit looser, because then that might make it, you know, it'll loosen the damping, so it might oscillate a little bit, but then it might help reduce that, or you can try strengthening it.
Just one.
Yeah, one or the other.
Yeah.
That's to go one or the other.
What about, would you know anything about like the tuning, like the software? Like,
Oh,
like,
no.
yeah,
Yeah, that might, I mean, that probably has a big impact too, but
Uh-huh.
that one. Yeah, that one I probably have less.
okay, I just thought I'd ask, because I was like, wow, that's what we're learning, like, it's over and
Yeah,
under
yeah.
damping, like,
No, yeah, no, I think
funny,
that's a great example. Sure.
all right, thanks.
Yeah.
Trying to solve this problem
Okay.
with this way, like I break it like smaller.
Yeah, you can do that too. Yeah.
I get a different result.
So hyperbolic sine. So one of the results we got was hyperbolic sine. Hyperbolic sine is just a combination of exponential terms, right? So sine h of t is nothing more. I think it's like e to the t minus e to the minus t divided by 2, something like that. So
Oh, yeah, I got
so
that one.
yeah, so then if you
I
plug
got
in
that.
hyperbolic sine is equal to that,
Yeah, I
then
got that one.
exactly. So yeah, so I did it this way just so that we get practice with the kind of the quadratic denominator, but you can absolutely split it up like that.
Yeah, that's why. All right, thank you so much.
Yep.